Okay, so this section here really is small, and if you've actually printed off some of the future sets of notes, many of them are like it's not a very big unit in terms of how many notes we have to do. This unit is almost entirely math based. There's very little, if any, theory to it, which means that most of my notes are basically I show you a few examples, and as long as you understand how to do the examples, we're kind of good to go. So, anyways, here's our topic today. It's called percent yield, and I want to start off by making sure you guys know the difference between percent yield and percent difference. Okay, there are two different formulas. I'm going to extend my page here. We've already shown you guys how to do a percent difference, and I often do this in labs. Percent difference is where you take what you actually got in the lab, you subtract what it theoretically should have been, you divide by what it theoretically should have been, and you times by 100. That's percent difference. For example, you guys did this on a lab where you calculated the value of R, and I still have to mark that lab, but it should have looked something like this. What you guys actually calculated, I want to think was about 8.5 or 6 maybe. It actually should have been 8.31, and then you divide by 8.31 and times by 100, and your percent difference would have been like, I don't know, 6% off. I don't know what the number was, but somewhere in that ballpark. Okay. Percent difference basically is how far off of the number that you're expecting are you. Okay, and this can be either a plus or a minus number. If you are over, it's a positive percent difference. If you are under, it's a negative percent difference. And the way I like to describe this to kids is think of how you do a test. Let's say that the test was out of 59 questions, and you happen to get 57 of them right. Okay. It's not your percentage I care about. The question is, what percentage were you off by? And so what you do is you'd say, well, you got 57. You should have got 59. When you divide by 59, this is your percent difference. I'll just calculate it real quick. 57 minus 59 is minus 2. Divide by 59, I get negative 3.4%. Why is it negative? Well, on your test, you were low by a certain number of questions, right? I mean, on a test, you can't get over 100% in theory, right? So you were off by 3.4%. What it really should mean, though, is that your actual percentage would be just to take this and divide them by each other. 57 divided by 59 means you'd have gotten 96.6%. This is what we calculated as a percentage, but this is what you were like off by. What do these two numbers add up to give? 100%, yeah. Percent yield is basically a traditional percentage, A divided by B. And it just tells you what your percentage is as a number, ideally out of 100, because normally you're trying to get 100%. A percent difference then is how percentage far off you are. So if you got 96.9% as like your percent yield, then you are off by 3.4. If somehow you could get 103%, then you were off by plus 3%. So percent difference is how much you're off by. Percent yield is basically a traditional percentage. So all you got to do is figure out what you actually got, what you should have got, and divide them by each other. Now, in a lab setting, we've been working so far just on this. When you guys were doing your work, like doing math, like on the previous slide here, we were calculating how much theoretically we're supposed to get. Sorry, give me a sec here. We were trying to calculate how much theoretically we're supposed to get. But the truth is that might not always be the case. And the reason why is that as I wrote these equations right here, we assume a 100% yield. Does every equation, though, happen 100% of the time? And we already know that that's not true because we learned about how strong and weak acids, strong acids, they ionize almost all the time. But if it was a weak acid, it might only ionize 5% of the time. And so I might only expect a 5% yield. Does that make sense? So for the most part, when we do a percent yield, we're going to compare it as though ideally it actually was 100%. But as you write an equation as A plus B turns into C, this number right here, this percentage, is really what we're calculating. You see what I'm saying here? So when we do a lab, what we're going to do is we're actually going to calculate how much product we make. So how much we get when we do it in the experiment, theoretically, is how much we expect it to get as its maximum under 100%. That tells us our yield. So it's super easy to do. So Let's do, I think I've only got like, what, one equation? One example? Yeah, one example. So here's what we're going to do. I'm going to take 6.78 grams of copper, and I'm going to tell you it's what's produced when we take 3.94 grams of aluminum and react it with copper 2 sulfate. So first thing we need to do, just like we did in our previous slide, we need a balanced equation. So I'm going to take some aluminum. I'm going to add it to copper 2 sulfate, and this is my recipe. Hopefully you'll recognize that if my goal was to make copper, this is one of many recipes that would make copper. Because this is going to be what, a single replacement reaction? So under the single replacement conditions, it would make Al, let's see, 2 SO4 3, and the other byproduct will be solid copper. Why don't I call these ones aqueous just to make sure I'm writing a statement down. Quick review. I know this isn't the point of my lesson here, but who's the spectator ion? Can you guys pick out who the spectator ion is in this equation? Yeah, SO4 sulfate. Because really, I began with some SO4 right here, and I ended with SO4 right here. It didn't actually change. So it really isn't necessary for it to be SO4. I gave an example on Thursday of how if you were baking, does it have to be butter or could you use margarine instead? You could use the same thing on this example here. Does it have to be copper sulfate? Probably not. If I were to use copper carbonate, all that would change is that this would become aluminum carbonate. But like, would I still make solid copper at the end of the day? Yeah, sure. But anyways, the only reason I need this though is to balance it. So to balance, I need a 2 here, a 3 here, and a 3 here. Are we okay with that part? Okay, first question's really easy. What is my actual yield? No work for this. Literally, we have to look at the question. How much should I actually make of copper? Yeah. So I actually told us that. Now, when we do our lab tomorrow, though, how are we going to calculate this actual yield? What will we do? We're going to weigh it on a scale. Yeah, we're going to do a chemical reaction. We're going to make some product, and we're going to weigh it on a scale. Okay. The theoretical yield, though, is how much could we have gotten if it had a 100% over our arrow? We're assuming that this is 100%, but that's not always the case. So let's find out what this percentage right here on top of the arrow should be. So to figure out the theoretical yield, now we do the stoichiometry like we normally do. So if we started with 3.92 grams of aluminum, we need to divide by aluminum's molar mass. We need a ratio, and then we need to use a molar mass for whatever it is that we kind of turn it into. So now I'll use a new color to help keep straight here. We need right here for it to be aluminum's molar mass, which is 2698. Then for our ratio, we want to get rid of our 2 aluminums, and the relationship between aluminum and what we're looking for, we were trying to make copper, is 3 coppers for every 2 aluminums. And then the final step here is that copper was, its molar mass is 6355. So long as you're getting pretty good at this process here of kind of writing out these string of numbers, I don't want to say that it's getting easy, but hopefully it's very redundant and you're like, okay, I know all these steps because it's the same thing more or less over and over again. My goal now is to try to teach you how to deal with all the little tweaks you have to make. And so the first tweak right now is, well, what happens if it's not 100% yield? I got a theoretical yield of 13 point, I'm not going to round it yet. I got 8500, something like that. Let's get that. So here's the thing. We assumed that all of this aluminum turned into copper. I'm going to use my hands here. We normally like to assume that as we have a reaction, I'll do it from your perspective, this is your reactants, this is your products. We start with all of our reactants and we start with no products. And as the reaction takes place, this is what happens. And when you're done, this was 100%, this was 0, and when you finish, everything has changed. That's not always true. Sometimes it works more like this. or like this. Where when you're done, you still have some reactants left. You still have some products left. So to figure out the percent yield then, we only got 6.78 grams. We were expecting 13.850 grams. So divide those times by 100. I got 40, how many sig digs do we get? 3. I got 49.0%. Well, because what I had here was 0.4895. Did you get that value for 0.4895? And then with 3 sig digs, I get to keep these 3 sig digs. This 5 then rounds the 9 up to a 0 and a 90. So 49% yield, basically. Which I tried to prep you guys a little bit for this in our previous units, the idea that not all reactions react 100% of the time. So this is one of the ways that we experimentally figure that out. Sound good? Okay, last slide. It's all just theory knowledge, basically. The question you'd have then is, well, why is it not 100%? And in a way, we're talking about efficiency. For some reason, during that chemical reaction, something became less efficient. And then there's many reasons why. Here's 4 main ones. The first one is that when you're measuring, you guys know this in our labs, I always ask you to talk about the accuracy and precision of our devices. When we think about it, sometimes our devices are not perfectly accurate or necessarily very precise. And so measurement uncertainties are one of the reasons why we might not actually have a perfect yield. It might not necessarily be your fault, but the scale you're using isn't good enough quality. That makes sense. 2, we like to assume that we work with chemicals that are 100% pure, but that may not be the case either. When I give you guys what's supposed to be like 100% pure barium hydroxide, it might be 99.7% pure. Again, think back to if any of you guys watched Breaking Bad, that's why Walter White was so good, is because his crystal meth was almost entirely pure. There was no extra stuff inside of it. So, 3, I need to, sorry, my voice is really going, isn't it? It's scratchy. The term is called washing a precipitate. Can you guys write down next to it? Washing a precipitate is a fancy name for filtering it. Okay. When you finally create a precipitate, some sort of solid device, we have to separate it. And the most common way of separating it is normally filtering. Ideally, a filter will be perfect, and it will only trap the molecules you're looking for, and the rest of the molecules, usually water, will go through the filter. We're going to see in a lab that we do in a couple of days that that's not always the case. So often when you're filtering, sometimes through that process, you lose a few particles. Does that make sense? We call that washing precipitate. And then the last one is basically the main focal point we've got here, is that we always assume that a reaction happens 100% of the time, but some don't. Some reactions only happen 5% of the time because they're, say, weak acids versus strong acids. So it's not fair to assume that it always starts 100% zero and does this. Sometimes some reactions only happen a little ways. Let me give you one final example, and my voice is going to run out. Aluminum. Aluminum rusts, if you guys don't know this. But one of the cool things about aluminum is that when it rusts, it puts a coating around the outside that's clear, and it doesn't flake away. And so as aluminum adds to oxygen, it makes Al2O3, but it only covers the very outside portion of the aluminum. And so, like, maybe 5% of your metal will actually rust, and everything that's on the inside, if that makes sense, will stay pure aluminum. Iron is different, however, and copper is different. When iron and copper rust, it becomes very flaky. And so, yes, the outside coating will rust, but then that outside coating will probably flake away and scratch off, revealing the next layer. And then that next layer will then rust, which will eventually flake away and reveal the next layer. Does that make sense? And so, if you kind of get what I'm talking about here, things that are made of iron and copper, you can actually rust them away to entirely nothing because of the fact that they flake away. Whereas actually the rust of aluminum oxide is actually stronger than the aluminum itself sometimes. And so only like 1% of it will rust. And the inside core will remain just regular aluminum. So we can't know that. I have to tell you the reaction completion, or you guys have to like solve it in the lab. Okay, I'm done. My voice is done too. You guys have any questions? Okay, so a couple thoughts. We're doing a lab tomorrow, so you guys can print that off and start looking that over. You can probably do a large chunk of the assignment. There's only 7 questions. You can start looking at that. Or if you guys would like to work on math, because you can do that as well today. So I'm going to stop talking.